Okay, welcome back. Our second speaker for today's morning session is Soham Ray from IIT Roorkee, who'll be talking about the complexity of interfacial slip.
Hello everyone. So I'm Soham and I'm from IIT Roorkee, and the departments that I work on are earthquake engineering and School of Data Science and Artificial Intelligence. So little bit about IIT Roorkee, and as you might be aware, it's a remarkable place for both engineering and sciences, given there are a number of departments focused towards earth science, mechanics-based studies, and particularly earthquake engineering department has a culmination of three sub-disciplines with very strong focus in structural seismology and soil dynamics, completing all the aspects of the earthquake. Yeah. So, and I thank organizers, in particular Debayan and others, for giving me this opportunity to talk about this work. And this is mainly about the interfacial slip and how slip conditions or the interfacial conditions dictate sometimes a faster movement, sometimes a slower one. And yesterday we did see Kaushik's talk on how the bulk and interface combine together to give a fantastic range of motions phenomena. Tweak my talk little bit after Kaushik's talk yesterday, so I focus more on the interfacial properties rather on the bulk ones, and we see that there are various realization that simple laboratory based frictional and strength formulation allows us to do so. So bit of a motivation first, and that you are aware that the subduction zones and these are can host remarkably host of lots of motions. I mean, so from very slow and locked at some portion, still pushing by, and all of a sudden there is over a very short time scale there is a rapid motion, and that cascades like lots of other processes within the earth. There's slight error in this, so I'm not going to that detail, but yeah, so let me replay this one. So you see the scale goes like years and years for like 100, 200, and then suddenly within a seconds you get an instability, which we call, and that kickstarts an earthquake that propagates through the medium, and that creates like tsunami and other things. And on the left, again, maybe a appropriate citation is required, but it's pretty standard in our community that all of these motions have a strong bearing on the interfacial properties and how they looks like. For example, whether there are frictionally stable regions, there are asperities which considered as frictionally strong, and how they are distributed, their sizes. So there are lots of controls, and in terms of physical processes, there are like fluid flows within that. There are a diffusion of pressure that changes the strength conditions, and the range of physical processes are enormous. But in this talk, I will touch only the bare bones modeling choices and its consequences, and simple modeling choices, and that we'll see. So maybe a little bit more pictures. So what happens, we also get surface indications. For example, the figure in the between and maybe in the left. So let me try to run it. So you can, so they have surface indicators. For example, after an earthquake, you can see there's a split apart. So let me try if it runs. Yeah. You see, so this is on the surface. So whatever happens like 20 kilometers deep, you not only get in waves, but you can get an actual motion. And again, these are taken from various standard sources in our community, and so yeah. And what happens at the base are like there are lots of motions that happen, which are recorded on the top, and these circles indicate the depth and the magnitude of such sliding motions. Point is, whatever happens, there is some relative sliding happens within an interface, which is hosted within an elastic medium of rock. So point is rocks can store energies, and they can release energy. And when they release energy, and what we feel are the seismological elastic waves, and this is the part of seismological studies, and these are standard, our inertia, then body force, then the divergence of the stress. You can use simple constitutive elastic relation to and put it back here, and you get two kinds, at least, transverse longitudinal waves. But the focus of this talk is not to simulate elastodynamics through the earth, is just to make the point that this is the source of all the waves. And this source in seismology, when viewed from a little far, just like we view a coffee mug, a warm coffee, it has a molecular motions which average out to form a macroscopic temperature. In same way, there are lots of phenomena happens within the earth, which in the fault there are sliding, there are slip, there is a rapid slip, there is slow slip. All those are while you model elastodynamics through the earth, then we club in one body force term, and they have their equivalent representative. So this talk is not about how waves propagate through that. This talk is mainly to concern the sources of such seismic waves within the earth. Okay, so again, the bottom line is there are so there are a substantial sliding motion, slip motion goes on, which we want to understand. And so this is, they can have in openings, mainly these two modes we mainly talk about shearing. So let's march forward. So simply speaking, although fault zones or any interfacial geological condition, they have damage zones, but we for now neglect these damage zones. Reason because there is a slip localization phenomena, and we can consider that a fault, geological fault, or a landslide kind of a setting as just a slip on a mathematical plane. By slip, I means there's a relative displacement between two surfaces which slide past each other, and this is the definition of the slip, that's a relative displacement. And the damage zones, although they are wide, the actual slip zones are very, very thin, and so this idealization is not very far from realistic conditions. And also realize that a part of the fault or part of the interface can be slipping, and the other part can remain relatively still and not slipping at all. So you see that you can think it in terms of the thermodynamics, that one part is fluidy, other part is little bit frozen, something like that. So yeah, in that sense. So slip we defined, slip is defined as we are aware. Then there are tractions that are resolved at the interface, and that traction is whatever the external tectonic loading conditions or some loading that we saw yesterday. So in absence of any slip, so there is no slip or maybe just uniform rigid, so we just get traction equal to the any external or traction realized at the surface, any external traction applied. But if there is a slip happens, then we get a change in the traction from external to some other quantity which is slip dependent. So this is purely due to deformation, and we can model this elastically. So there is a relation between the traction at the base or between the interface and the slip that happens. Okay, and the closer condition that when a fault slips. So one closer condition we can put in terms of simply that the stress that is at the interface is equal to the strength of the interface. In this case, maybe it's purely frictional. Okay. So going ahead, so just to motivate this further, it's in its right. There is we can discuss it maybe for an hour. The phenomena and the dynamical system that permits a localization to solutions which are mimics just a planar interface. So those are also observed that there are damage zones, but actual slip zones from the core studies, they seem very thin. So this situation like damage zone not considering is not, it's not remarkably oversimplification. It has quite a bit in it. So yeah, talking about faults, in what way? So it can be anything. For example, there's a half space just about a rigid. So this all part is rigid, and this is deformable half space. And if you follow the literature a little bit, so there are ways in which you can actually express the stress at the base as whatever stress we apply, and a slip dependent, in fact gradient of slip dependent, Hilbert, this is a little bit singular as we saw yesterday as well. So it's a Hilbert transform of the slip gradient, and you see this is a singular integral. And because it's integrated throughout, you see there is a non-locality involved here. So slip at one point affect the stress at the other point, or stress at one point affect the slip. So it's like that. So keeping this little bit aside, although it's a very nice relation, but we may be preferring simpler relations. For example, for this kind of a thin slab or a slender object there, so maybe it's a landslide or a glacier mass, the relation is remarkably simple, just a Laplacian of the slip. So I forget to write the relation here, but I think it will be coming soon. Yeah, yes. So the same stress at the base, whatever stress we apply in the form of either loading or through velocity, is equal to external plus any elasticity driven, and we can do elasticity driven stress changes, and we can do a simple force balance, and we can see that this is place. Force balance, while we're doing, we can consider it some depth averaged form, so I'm not going in that detail. So point is, we have elasticity, interfacial elasticity is different. The formulation looks different, and these are just two end members. So one is thin, one is infinitely thick, like that. Now let's come little bit on the strength part, and you see this is the strength of the interface that can, this is the simplest possible strength that that there is a slip happening, and all we found that the when stress is equal to strength, the strength is just one number, residual tau r, and there may be a background, so tau x is tau b, there's a background stress, and at the interface we get tau r, and we can solve this simple relation to find a slip distribution like that, where at plus L and minus L slip goes to 0. So this is the scenario for the strength, which is just this dashed, this red line, not these two. So you see this is like a singular crack, there is a stress drop here. These are the external stresses, which is tau b in this case, and you find a slip distribution, and the stress looks like, so it's a crack. It looks like a crack. But what about the propagation condition? How we know that this is a crack and it will going to propagate? So we need something else. We'll come to that. Just to complete the picture. So when we have other strength formulation, that is strength is just slip dependent, like EDA 1977, Rice, and those model Dugdale Barenblatt types. So you see when we have going all the way weakening, then we can have this kind of so singularity is taken care of by reformulating a cohesive zone kind of a strength formulation, and we do not have infinite but a finite, but tau. So these are tau p. So we can have tau residual and tau external outward, and when, so this is the model 3 where we drop and then settles to a one particular place. So these are slip dependent constitution formulation, and they'll crack it, and you see this is different profile here and profile here, so there is no stress singularity here anyway. So again, so what's the propagation condition? And that condition we can simply formulate in terms of let's do this for just to problem number 1. So we can solve this part. We can compute energy density because we know what are the stresses inside this. Once we know the strength density, we can compute the what we call um, total energy, internal energy. So point is the bulk can send energy if there is a crack available, and when the crack will grow, that is that energy is expended to increase the surface length or surface area. So that calculation we can do. So it's just energy which is expended at the whole crack of length L. So we get this formula, and suppose we know what G sub C is or G sub C, that is the fracture energy here. So we can get critical length after which a crack can propagate. In this way, formulated through the one parameter G sub C. So there are other ways to go for. So I just chose the simplest possible relation, which is not often chosen, and these are the models that people generally go for. And we'll come back to this part, although it's just a slip dependent strength, but it has a it captures all the bare bones or the essentials of crack propagating. So once we have a sophisticated strength, we will have the same or more lab-based strength formulation. We'll get a different LC, but point is there exists a critical length for a crack growth. So let's move to experiments a little bit. So in lab experiments on just sliding blocks, it has been seen, I mean, on a range of rock samples in all labs performing these experiments, that the frictional strength between the rock samples are sliding rate dependent. And you see, for any sample, for example, there is a decay in the strength for many samples. So this is like a weakening with respect to sliding rate. And there is another form of weakening which happens around seismic speeds, that there's a further weakening. So we are not going in this detail. Let's have a low sliding rate formulation and see. This is called as velocity weakening. So your strength depends on maybe the pore pressure, or you can just ignore it for a while, and if effective normal stress, then friction coefficient, and friction coefficient indeed has a sliding rate dependence, so it decreases. Our story is not over here. This is a little bit of an ill-posed problem. We can discuss it length if time permits at the end of the talk, and how this ill-posedness is removed by just having two effects. So indeed, many rock samples do show that there is a velocity weakening, that your frictional strength weakens with sliding rate, but they do so not directly, but by two effects. First, we call this a direct effect, that is a increase in the strength, then a subsequent evolution effect, that is a decrease of the strength. Okay. You can plot the same thing with respect to slip. So suppose the two rocks that we initially were sliding at one velocity, and later little bit higher velocity. So first the rock samples were sliding at this velocity, and there we multiply by factor v and sliding to the higher velocity. The moment there is increase in the loading rate of the or the sliding rate, we get a sudden jump in the friction value. And so there was a friction value for this particular sliding rate. We get a sudden jump for due to this increase in the sliding rate, and that and it doesn't stay there and rolls to a different steady state. Just note that this is a velocity v corresponding to this sliding rate, and this is FSS or steady state friction corresponding to this sliding rate v over small v. And important to note that these two are not identical, they are different, and this evolution needs an equation of its own. So there is a direct effect that takes care, and an evolution effect, and this inclusion of a delay term or memory term actually regularizes an otherwise ill-posed problem, which we'll discuss some other time maybe. So please feel free to interrupt me, because there are tons of details around these places. So steady state friction theta looks like this. Okay, and B and A are the coefficient by which the eventual weakening happens, and A is the direct effect, which is strengthening. So yeah, so this is not very different from what we just saw with the slip weakening form. So it's a slip weakening. Here also there are slip weakening, but it happens through a different mechanism, and they have a bearing in what we understand about the earthquakes and how they start, how they nucleate. So yeah. So going further, I think this pictures explains pretty much everything, that if you change the sliding rate, your rock samples show these are experiments, real experiments, so no words required. So this is what we see, people see, that's we see. So going into the details, so if the direct effect is subdominant compared to the eventual weakening, these are the scenarios which is referred to as rate weakening region, and they are the ones which are responsible for rapid sliding. If the interface has this property, they are the ones that provokes earthquake. The strengthening regions are the one where stable sliding happens, but the story is more complicated than this. So just having a rate weakening region does not guarantee that you're going to get an earthquake. As you see that there should be an energetic condition, your length of the crack should be large enough so that you can grow the crack eventually. So how these translate to this lab-based formulation, lab-based friction. So bottom line again is friction is just not one number. It has a sliding rate dependence and a state dependence on that. Okay. So here we start to couple or start to understand. We take a simple model. You can take an earthquake, you can take a landslide type of a case, a simple relation between the stress, traction at the base and the slip. So that's elasticity. You incorporate a closer condition that this is equal to the strength, and the strength is given by rate state dependent. So when you rearrange the terms, you get a differential equation that looks like a partial differential equation that looks like this. Okay, so that's coupling. So let's say we just simulate it, and we can have a various realization. So before going to that, so what we say that we coupled elasticity, which can be earthquake types, landslide types, with the strength, and we formed a PDE. And these are the length scale that comes from the coupling of elasticity and the frictional thing. So we'll come to that. So the acceleration looks like that, and we want to know that under what condition the sliding rate can become faster, slower, or what that. So what we do, we go for simple dispersion relation, or you can call it a dispersion relation, stability analysis, scaling analysis, that goes by simple name. But what I feel, we just substitute the corresponding eigenvalue of this operator, making the whole extended body shrink to just a spring block, and that is the dominant, and this is the dominant, this is the one wavelength. Okay, so when we do this, we find that one of the modes could be written just like that. And you can see here that the sliding rate with respect to time evolves through this situation, and a positive of this bracket ensures that it grows with time always. So that gives you an indication that wavelength of perturbations that you do, if it crosses this limit 2 pi times some length scale, that length scale is coming from friction and elasticity and this friction, then we can get our slip rate to grow faster and faster with respect to time. So this is one condition. So we need rate weakening patch, as well as we need the wavelength of perturbation and or the length of the rate weakening patch long enough to permit any kind of growth in the sliding rate. Okay, so going forward, so again, simple model that we had, we find that we need a rate weakening patch, and the wavelength of perturbation exceeds this elastofrictional scale, then we can get slip to accelerate, and they accelerate via this v square by v square. So it scales with a square of the sliding rate. That indicates that this problem, so this is simple elasticity. This is lab-based strength formulation, and this permits an instability in finite time. And this finite time instability is the reason that we get an earthquake. So interfacial may be sliding slowly initially, then at some stage it started going faster and faster, and that instability is reached within a finite time, and we get a massive sliding rate that provokes the inertia of the top layer, and which permits the transfer of the waves. Anyway, so we can use this, and let's try to see what simulation suggests. So you see, I give a loading rate. There is a frictional value here, A over B, and given a loading rate, you see there is a unbounded growth of sliding rate. So this is, and it happens over a patch length. So we need a length. So what the singularity indicates, this singularity, see the scale, indicates that the physics is changing in the problem. So now we need to incorporate some other physics, but what it tells, it resolves all the conditions that permits a slip rate to grow. So you need a large enough sliding surface which has a rate weakening properties. If this is large enough and that's quantified by the elastofrictional scale, then you get a singularity in the sliding rate. And that singularity is an indicator that your fault is now ready to dynamically propagate slip and become the source of seismic waves. Okay. So I'll come to this heterogeneity part in a second, but yeah. So resume so far, what we get? So we get that frictional strength is rate and history dependent. Elasticity and friction together gives a length scale for the problem called as elastofrictional length scale. And for this thing, the elastofrictional length looks like this. And for another end member where there's a more earthquake-like, elastofrictional length scale looks like that. And D sub C is the length which is coming from the decay of the friction towards a renewed steady state. So friction law is essentially giving this length, and because we have elastic models, so these things are coming in anyway. And what we saw that a minimum crack length or the minimum patch length is required to nucleate an unstable acceleration, which then becomes a source of seismic waves. And we also need rate weakening region. And that length slightly differs for different elastic configuration, but that is just details anyway. So story is that slip rate initially, if you give any perturbation, it localizes, then hits the patch. If you give a perturbation for a longer size, then it hits a patch and then grows. And if the inertia of the medium kicks in, and then that prevents the singularity to happen. But if you suppress the inertia or any radiation damping kind of a setup, you get an unbounded slip rate. So why this is useful? It's useful because it resolves all the condition for instability to happen. So let's go further. I mean, this is just another detail, just to highlight the importance, the why we see. So even if you give a perturbation over a very shrunken region, a high velocity and a very, very low support, very short support length, it expands. Instead, it contracts if you give it on a larger support length till it hits this length, and then only your sliding rate grows anyway. So model that we have so far is very simple. One elasticity and friction, they give one length to the problem. But this might be an oversimplification because earth crust subduction zones, they are, data suggests that they are frictionally very heterogeneous. So are there consequences of including a heterogeneity? By including heterogeneity in frictional parameters like those jump, rate, direct effect, and then evolution effect parameters, they can be different at different points on the fault. So is it unnecessary complication to add an heterogeneity, or having just homogeneity is a unnecessary simplification that we'll try to highlight given the upscaling theme of the this seminar or this conference. So one length scale we have from elastofriction. Now we are supplying from our side another length scale in the problem through the variation of the frictional properties. So frictional property may vary from, now the criticism is when in the earth we have such a nice sinusoidal variation in the frictional properties at the interface. We never, but from modeling point of view, a sinusoid gives me just one length. And in any other description of heterogeneity gives lots of other length scales. So this is just one wavelength. So I can actually see that how this varying wavelength interferes with already all the length scale that are already present in the intrinsic to the system. So one is naturally coming from the system, and one we want to test that what length scale interacts in which manner. So let's run this and see. So problem is again simple thin slab with rate state friction, but just the frictional properties are varying over one particular wavelength that is comparable to the elastofrictional length scale. So if you run, you see that now the convergence happened to place not at the same regime, but slightly out, not at the place where we want the earthquake to nucleate, but at place somewhere else. And it traveled a distance, considerable distance. And you find that it chose the most rate weakening region or in one part. So this is the part which is most slippery. All the fault is slippery, all the total interface, but it chosen one particular region which is most slippery, loosely speaking. So, and there we get unbounded sliding rate and that nucleus earthquake. Now we change the wavelength little bit, and we see that for a different wavelength, where we perturbed earthquake, the instability or the nucleation condition is satisfied at somewhere else, which is not the most slippery part of the fault. So you can clearly see that including an heterogeneity and including an additional length scale in the problem interferes with the elastofrictional length scale to give richness of the it's not straightforward that the most slippery region will take off. Also, coming back to the point that Professor Vikas mentioned, that if we have two cracks in a same sample, the longer one will go. But if the cracks are evolving itself, and the shorter cracks can get kicked because they are reaching at they are reaching first. So this is one crack solution, as I'm coming to this in a while, why this can be a solution. And this is another crack solution, and you see the one which is the short of whose length of the crack is small are the preferred region for instability to flourish. So that's little counterintuitive. So yeah, so point is I marked them by green part where they support lots of support flux of energy in that patch, or you can call it the earthquake nucleation around there, and these are forbidden regions. So let's try to understand. So now is the situation where you want to inject more physics into the system, like include pore pressure, include more variation in geometry. So you can complicate the system as much as you can, or an alternate route could be to let's understand why this is happening from a different perspective, or from maybe, yeah. So we know this part that that sliding rate which we saw is scales as v square when in a rate weakening patch, given there is a sufficient length to do so. And so we can think ansatz for a solution of sliding rate as just one distribution over time to instability. And we see that, and we just solve for these distributions. So if it's a homogeneous fault, throughout there is no frictional property variation, then one solution can be translated for translational invariance is there. So one solution is for all of the translate the faults. So there is one solution only. However, if there is heterogeneity, you break the translation invariance, and as a consequence, you get two two solutions in this case, one at here, one at the top, and at one at the crest. So this is consequence of just broken invariance in spatial that now you have two solutions for that, and there is method to how you can find that. So what to do now, that how to understand that this out of these two solutions, which one we should be going for, and which one maybe a evolving simulation will get into. So to do so, we now move to a self-similar system, because I forget to mention that these blow up, or the singularity self-similar blow up, so we can exploit that property and go to find the similarity variables. And this is pretty much straightforward, how we come from a time-like variable to a logarithmic of time-like variable. So you can think there is a singularity in the sliding rate.